Hello everyone, this is a write-up for the challenge Bug Squash Part 2 from this year's Lead Up CTF. So after downloading and unzipping the attachment, we can check out what's in there. And it's looking like it's a Unity game. So we can see here the Unity player DLL, which gives it away a bit. And normally reversing Unity games is pretty straightforward because the .NET DLL can be decompiled to pretty clean C# again. But in this case, the game uses IL2CPP, which is a performance improvement for Unity. So the idea is that C# code is compiled into IL, so intermediate language, and this is transformed into C++ code, which is compiled to a native instruction set. And we can see that if we go to the game data folder, and we can see here there's a IL2CPP data folder and also the game assembly.dll in the root folder, which is not a .NET DLL. So reversing that is a bit more tricky because we don't get the nice transformation back into C# code. All right, so let's have a look what we actually have to do. So in the description, we can see that we have to score more than 100,000 points, and we have a time limit of 2 minutes. All right, so to get a better overview, we are using Cheat Engine here, and we attached Cheat Engine to the process, and now we can use dissect mono to get an overview over the classes the game is using. So if we look here, we can see basically there's like an audio manager class, and we can drill down to the fields. We can see audio manager using 2 fields. We get the type of the field, and we get the offset where the data is located relative to the base object address. So that's interesting because later, if we want to understand the disassembly better, we can use this as a reference and see where the writes and reads are going to. So yes, and we can get a list of the methods for each class. We can see here information like return type and the list of parameters, and we can right click on each of them and get the disassembly of the JIT. All right, and with all this, we can have a look at what else the game is using here. So we have a bunch of classes, and there is some interesting ones. Maybe Game Manager could be interesting. So we have the player controller, which is most likely the movement of the player and collision. We have 2 classes that are concerning bug movement maybe and how new bugs are spawned. That could be also interesting. So we see here something interesting. There's a server response and there's send points to server that is pointing out that there is like some communication with a server in the background. So it's not a game that's completely running local. Okay, so let's see what we have. We can take, for instance, a look at the bug spawner script. So we have in total 5 methods here we can look at. And for debugging, a good starting point might be the start and the update, because the 2 methods are a bit special in Unity context. So the reason is that Unity uses a set of special methods which are controlling the life cycle of game objects. And if you have a look here, we can see basically there's the start, which is used in the object initialization phase, and it's called once. And then we have further down, the update method, which is called every frame. So there's more of them, but in this case we have start and update. So what we can do now is to open the disassembly here and set a breakpoint. And if we activate the game, so it's ticked once again, we can see it's breaking at the update call because there's apparently somewhere a game object which has this script attached and it's ticked every frame. So yes, and to make more sense out of all this, we need to have a good idea about the calling convention. So we know where to look for certain information. So the idea basically is that if somebody is calling a function, there might be parameters to pass in, and the function itself needs to know where the parameters are to be found. So they could be on the stack, for instance, or they could be in certain registers, and that is basically all written down in the convention, which the caller and the callee are implementing both. So we can have a look at this side here, and there's a good outline of all the registers and the attached semantics basically the registers have. So we have integer arguments, for instance, passed into RCX, RDX, R8, and R9, and RAX is used as the return value register. So that's interesting because we have a method which is bound to an object, and the first argument is basically the this pointer. So the base address to our object is in RCX. So if we go back, we can see here that basically RCX is written to RBX, and later on we have reads from RBX with a certain offset, and this is basically reading the field data of the object we are calling the method on. So for instance, we see in the next line there's a read from RCX with an offset of 4C, and if we recall the list of fields, we can see that at this offset there is a field value which is called timer, which contains a float or a single, and the value is read here and stored in XMM6. And next there is a call to time delta time, and this function also returns a value, but this time it's returning the value in XMM0 because it's a float value. And we can see that by checking out again the calling convention, which says basically that floats, doubles, and stuff which are non-scalar types are returned in XMM0. So we can see here that XMM0 is containing the delta time. So that's basically the time that passed since the last update call. And XM6 is containing the timer value we are tracking over time. And we are adding to this value basically the delta time on every update call. So what we can do now is to write it down in something like C# like code. And what we had here is basically timer, which is incremented by time delta time. That would be the equivalent of what we just read here. All right, next it's reading from RBX with offset 48. So we can again check here and see that there's the spawn interval and doing a compare with the current value of XMM0, which is the incremented timer value, and writing the incremented timer value also back to the field memory. And then there is a jump below, which uses the result from the compare right here, and it basically jumps out of the function if the incremented timer value is below the spawn frequency. And if it's not below, so if it's equal or larger, then we would end up here and calling eventually to the function spawn bug and spawn a new bug. All right, so we can go back here and write it down. So it would be something like if timer is greater or equal to spawn interval, and then we are doing a call to spawn bug. And we can see here that the first parameter, the RCX, is set to RBX, and we know that RBX is pointing to the current object, so to this pointer of the object. And since we are calling a method of the same object, we just set RCX to this pointer again. That's exactly fine in that case. And then it's doing two reads to some memory regions, and we can see it's already resolving the values for us. So it's two float values, 5 and 1, which are stored in XMM1 and XMM0. Then it's writing to RBX offset 4C, which we know it's the timer, so it's resetting the timer to 0, and then calling random range with the two values here. So we would have something like resetting the timer and then random range with min value of 1 and max value of 5. And then the range, which is returned in XM0 again, is written to the object field on offset 48, which is, we already saw that, the spawn interval. So it's resetting the spawn interval to something different here. So we are not spawning in the same intervals, but the interval the bugs are spawning changes over time. So one thing we could try is to change the spawn interval in which the bugs are spawning. So for this, we would go to the address where the max value is stored, for instance. And we can see the 4 bytes here are equivalent to 5 as float, but we can also just change the display type to float, and then we can try to type in something here. That's not working because the page protection is read-only, so we set it to read-write, and then we can change the value to something really small and see what's happening. So you can see there are definitely more bugs spawning now. That's nice, and we get a better score now, but it's probably still not enough to reach the 100,000. And also, if we keep an eye on the score, we can see it's resetting to 0 for some reason. So we should also investigate this. So after a while, we should have a decent overview of what's going on and should reverse some parts at least to see which parts could be interesting, which not. So the problem here seems to be that the flag is not stored anywhere locally, but seems to be stored on the server. So the idea would be to trick the server into thinking that we have a high score and maybe giving us the flag. So for this, we should next concentrate on trying to see how the client-server communication is working. So the interesting part seems to be somewhere here in Game Manager. So we should check out what's going on here. So we are currently here in the constructor, and you can see that there are a couple of field initialized. So we have a write to RBX with the offset of 4.0, and that's gonna be the session duration, which is set to 60. Then we have here a load of offset 48, which is the server URL, and it's written to RCX, and we are loading the string value from this address, and we're gonna check out what's written here. So in fact, yeah, this is the server URL. That's nice. So we're gonna copy that out. That's gonna be helpful because now we know at least some parts we can talk to. And what else do we have? So we are setting the retry interval to 10. So then we have the send points to server, which could be interesting to us because that's exactly what we want to know, how we can send points to the server. We have session countdown and we have start session. That seems to be like the timeout, which is ticking down. And if we check out the code, we can see it, all the functions are looking more or less the same. It's pretty identical. There's not much information here, but the reason is that these are implemented as coroutines, and we can in fact see here, down here, the actual implementation, the actual logic of the coroutines. So we want to see what's going on here, we can just check out the move next method of each of those. So for instance, for the send points to server, we can see here there's much more going on, and here are some nice looking function calls which look very promising, like some JSON which is serialized and some Unity web request which is done. All right, so let's see what's going on here. So we are having a Unity web request that's taking two parameters. In this case, there is the URL and there is the HTTP verb that should be somewhere here, and that's going to be a post. That's good. So we need to know that. Then a bit further down, there is upload handler set, which will upload the JSON data, and there's a download handler, which will give us the result. And there's a bit of error handling, which is logging an error if the request didn't work correctly, but that's all pretty much. So the only thing we need to know is what does the actual data which is sent look like. And for this, we just can create or set a breakpoint here and trigger it by squashing a bug. Now we should be in here. And now we are basically in time just before the JSON is created. So we step once and then we can check out whatever the result of the function is. And we can see here that's looking exactly like what we are looking for. It's basically user ID, which is sent with ID, and bugs squashed with the value 1. So let's write it down. So we basically know we are doing a post request to the URL here with that data. In fact, it's not exactly this URL. There should be an endpoint, and we can see where that's created. So we have the URL, which is at offset 48, and it's read here, in fact, and there's a string concat, so we should have the value here. Let's see. And that's exactly there. It is, so it's the endpoint update score. So we note that down. It's gonna be here. And that's all the information we need to update the score. That's nice. But one thing missing, of course, there is a user ID. So that's most likely attached to the session. So when the game starts, it requests a new session in the server, and the server will create a user ID, and the user ID will be valid during the duration of the timer ticking down. And afterwards, it's going to be invalid. So we cannot just keep on sending and increasing our score. That's at least a theory. So let's see if that's what it is. So we want to go to the start session coroutine and check this out. And we see here that it's also doing a web request, apparently. And a bit more logic. But here the request is created. So we can do exactly what we did before. We check out here where the URL is read and see what is attached to the URL to get the endpoint. And that's going to be start game. So we note that down. And we should have, we don't have any payload apparently, so it's just the call to start game. So we can in fact just try out if that's working, what we get. All right, let's just grab the endpoint and try to start a new game. And this looks actually promising. So we have a user ID created and we have a session duration, which is starting at 2 minutes. And we have a score of 0. So next we can try to see what's happening if we are updating the score. And we of course need the data. So we take the user ID and try to see what's going on if we send that as data. And we can see here we get a error and forgot of course to set the content type. And now we have updated our score. So we have a score of 1. So what happens if we send 10? Then of course it didn't work because anti-cheat noted that we sent too much. Let's see what's happening if we send 2. That's also not working, so we can only send 1, apparently. Okay, that's good. So we can now write a script and try to update the score as fast as possible. Maybe get the flag this way. Okay, the script is finished. So it's starting a new game. Then we grab the user ID and we sending a lot of requests, which should increase the score by 1. And hopefully that's gonna working. Let's see. And we can see here it's not working because anti-cheat is noticing that we are sending too many requests in a too short amount of time and resetting the score again. So that is also the reason why the score got reset when we spawned very many bugs. So that's not gonna work here as well. So we gonna need some kind of timeout and try to see what is the minimum of timeout anti-cheat is gonna let through. That seems to be fine. The only problem here is that it's so slow that we even here won't get the 100k points. So there needs to be, or there must be another trick that will give us the flag. Okay, so small disclaimer here. This was the point where I was stopping at the CTF and didn't solve the challenge during the CTF. But the solution is in fact that JSON supports keys that are case sensitive. So if you write something like this, then it would be a different key for JSON. And the server was implemented in a kind of weird way that it's gonna be looking at all the keys and doing a lowercase on the key and comparing with bugs squashed. So it would basically support this and would increment by 2 because there are 2 keys, and if we transfer them to lowercase, then it would be bug squashed lowercase and would succeed the test on the server. So if we run this, then we can see it's incrementing in steps of 2. So that was the trick. And the idea was now to put in as many variations as possible to get higher scores. Okay, so this is actually what we are doing now. We create a lot of combinations of the bug squashed key with upper and lower case and put all of them into the data we are sending, and that should be now basically increasing the score in very large steps. So let's see if that's working. I can see it's increasing. That's looking good. That should be easily in time limit. And there we have the flag. Nice.